Yeah, thank you. I'm Gerben Oostra, a machine learning engineer at Big Data Republic. And today I would like to share with you my journey in preventing churn. And that journey today starts in a casino. So imagine you're going to a casino and there's a slot machine with one nice lever, which we call a single one-armed bandit. We also have heard it in a talk before. But of course, this is a fancy casino, so that slot machine does have one lever. We've got multiple levers and want to choose which lever gives us the most money. But you can't make a casino of one single slot machine. You have got the whole bunch of slot machines. Each one built maybe in a different year, operated by a different operating system. So it's a little more complex situation. And solving that problem is the same as solving a churn case. And I will show to you today how those two match together. So back to churn. Churn really is a revenue drain for companies. Companies lose between 2 and 16% of their total revenue every month due to customers leaving, which is also referred to as churn. And therefore, it's a really high priority in all management meetings. They want to do something about it. And of course, the current age, we're going to use machine learning to prevent churn. And there are different ways you can use machine learning to prevent churn. And in common approaches, I see 3 big issues. The first one is to make a model which actually predicts churn. The second one is to assume correlation is causation. And the third one is that if you have your model, it tells you what to do, actually listen to it. And as a running example, I'll use a telco case where I got my most recent experience. So we've got a nice internet provider giving subscriptions to a diverse set of customers, all in the consumer market. So we want to prevent churn. The first logical thing you could do probably is create a model which predicts churn. So we got our historic data about people. We know what subscription they had, how much they paid, and we know whether or not they churned in the next few months. We train a model on it, so we get our nice churn classification model. We run it against our whole customer base, and then we get a predicted churn propensity. We know how likely everyone is going to churn. That set of probabilities we then give to our marketing department. They'll pick the highest one, are really creative about thinking about some treatments to do, some campaigns. For example, they can, if the customer is not worth it or the score is too low, don't do anything about it. They can send them an email, give some information, do a questionnaire. They can even call them up. Hey, how happy are you with our product? Can I help you with something? Or we can even visit them door by door and check if maybe their Wi-Fi needs some improvement. Give them a Wi-Fi booster. This sounds really nice, but actually the final goal we want to do is to prevent churn. But now we separate it in 2 parts. One part, data scientists predicting who is going to churn, and then we have a different department finding out ways to retain those people. But the people who are most likely to churn are not per se the people who we actually can retain. Those might be the people who think the price is way too high, they don't like the product anymore, or they already found a product from a competition. Or what we also discovered is, it could be, for example, old people moving to an elderly home. They're moving, so no way they're going to extend their internet subscription. So we really need to solve this problem as one whole thing. But you also might think, it can't be that bad, right? We've got our really good marketing department. They will find ways, and these are the examples I just gave probably are just exceptions. But something else also is happening if you just ignore the treatments you did. Because if you have your model and it gives for some customers really high score, you give those scores to the marketing department and they start calling them. And for some people, they're actually quite effective. So those are the people who are persuaded. After a few months, those people were persuaded, so after a few months they don't churn. So they end up in your future training data as non-churners. And therefore, if you retrain your model, it will learn that I shouldn't call those people because they have a low score. So your model will learn to tell your business to not call the people who you actually can retain. Inversely, the people who the marketing department couldn't retain, the so-called lost causes, they will actually churn and end up in your future data set as being churners. So your model will learn, I should really give those people high scores. So this doesn't really help your marketing department. So the solution is to solve it as one big chain. We want to prevent churn. We need to find out which things actually prevent churn. So we are going to. So what you could do is you predict the churn rate, or inversely retention rate, of every person conditionally on the treatment they got. So for the persons who got no treatment, what was their rate of churn? For the people who got a direct mail, and then you can find out what's the most effective one. But as a company, you actually have a special action, the do nothing. Because if we wouldn't have a model or don't do anything, then we always do the do nothing action. So that treatment is quite special. It's the baseline. It's not that we're sending somewhere else and we're choosing amongst these four. No, we have already chosen the do nothing action. And we want to know if changing our choice, actually doing something, has actually a significant effect. So as a business, we're not so much interested in the retention rate of the four individually. No, we want to know the difference between an uplift, or difference in retention rate between doing nothing and taking the action. Like how much does the probability of being retained is increased by doing our action. And that difference, that increase of retention rate, that's called uplift. So this is the target we are mostly interested in. And of course, if we have 4 predictions, we can quite easily calculate what is uplift. It doesn't really matter. However, if you have a model predicting an output, for example, prediction rate, the retention rate for direct email, and you subtract from it, and you're going to subtract from it the retention rate of doing nothing. Both of those predictions will have a certain error range. If you then subtract those 2 values, the error range will actually be added, while your values are subtracted from each other. So the error rate on your uplift will be higher, will actually be the combination of the 2 errors of your individual predictions. So doing that side step will actually make your prediction really bad. So it's much better to directly predict the uplift, and that can be done something called the transformed outcome trick, which I'll come back to in a minute, and it's described in this paper. Because we can do different treatments, but those treatments actually have different prices. Sending an email is way cheaper than visiting someone with a mechanic, truly physically visiting someone. So we want also to take into account those prices. And also, some customers have a really expensive internet subscription, and other ones have a really cheap one. So what we can do is we can take the uplift, which is like the increasement of probability of them staying, multiply it with the customer lifetime value. Then we know how much we will gain as a business from doing the treatment, subtract from it the cost, and that is the net effect of our treatment. And as a business, we can then choose the best one of that result. So while our model predicts uplift, the policy of doing actions we need to perform on the final net result. Then back to predicting the uplift. There are 2 steps. One, first transformed outcome, and while we're at it, we'll also deal with counterfactuals. So what predicting transformed outcome is this formula described in this paper, where I actually change from a classification problem, predicting retention, yes or no, to a regression problem where we predict uplift. And it's done by this formula, where Y is whether someone was retained or not, W whether they were treated or not, and a probability of getting the treatment. And if you fill in, for example, if for ideally treatment probability is 0.5, if you fill that in the formula, you'll get the 2, the -2, and the 0. So if you get treated, you get a regression label of 2. If you were treated and you were trained, you get a regression label of 2. If you were in a control group, so not treated, and then you still stay as a customer, you get -2. So it kind of feels like we don't want to have that. We don't want to treat those people. And if you churn, you always get 0. To see this working, actually this results in predicting the uplift, because uplift should be between -1 and 1, and not 2. I'll handle 4 cases. So for example, if we have loss cases, you've got a single user with certain features, and that person, hypothetically, is both in the treatment group and in the control group. And then, and both actually churn. both will get a label of 0. Your machine learning model, well, it's a regression problem, so it solves for root mean square error. For that set of features, can only give one prediction. If both samples have a label of 0, the best thing your model can predict is also 0, which is the uplift, because both in treatment and control, they churned. If, however, the one you treated actually was retained, we'd give that sample a label of 2. So for the same treatments, we got one sample label 2 and one sample label 0. Solving for root mean square error, the best thing your model would predict for that point in the feature space is +1, which is the uplift, because giving the treatment actually caused that person to stay. Inversely, if someone not giving a treatment, if someone not giving it, well, giving a treatment, they were churned, and staying in the control group, actually they were retained, you get the 0 and the -2, so you then go to -1. Well, the so-called sure causes, so it doesn't matter if you give them a treatment or not, they'll stay anyway. One sample will get a label of 2, other -2, and then you end up again at 0. Well, this I now explain it with one person, so you have like 100% or 0% of uplift. This you can also visualize, well, if there are groups of people and only a fraction of those people will be retained, then your uplift will actually be halfway, well, maybe slightly towards 1 or slightly towards -1. Well, this also, I now explained it with just one treatment. You can also generalize it to multiple treatments. So we can include our telemarketing, email, and visiting door-to-door. And then it just becomes this matrix. So using this transformed outcome, outcome transformation, we can then change our labels. We got all features, and we know for every sample we have in our data set, which treatment they got, and for each treatment, doing nothing, getting email, telemarketing, or door-to-door, we know if they were retained or not. And using this table, we can transform it into our new data set, where feedback on being in a control group actually is information for every other treatment. Well, and feedback on a specific treatment is only becomes in a new data set only a label for that specific treatment. We also see, well, so we now have, instead of a classification problem, we switch to a regression case. And now we actually have a multi-output regression case. And then in that multi-output regression case, there are missing labels. There are the so-called counterfactuals. We gave someone an email, but we didn't call them, and we can't afterwards have them in the same situation also call them. So, and actually those are the treatments we are interested in. So we need to deal with that. And that can be, well, if you have, for example, a neural network where you have three regression outputs predicting the uplift, and you have these labels, what we can simply do is make a mask defining which labels we actually do know and put the other ones at 0. And if we then multiply our output of our model with that mask, the output of the model for our counterfactuals, the treatments we actually don't know anything about, by multiplying that 0, they become always 0, and in our label set they're also 0. So the model will not get any feedback on those, but it will get feedback on information we do have. So the model is, we ignore any output of the model for treatments we didn't observe, and we only train it on the data we do have. And then, of course, during inference time, we just pick half of it and just take this output as our predicted uplift. So the first issue was to predict churn. Now it's clear that we shouldn't predict churn, because then, well, I just explained why we shouldn't predict churn, and better is to predict uplift, and that can be done using a transformed outcome trick, and we multiply it by the customer lifetime value and the cost to get our predicted action. And it closes the loop back to the casino, because our customers have different levers we can pull on, and every customer has a different reason how they behave on those. And then after we've pulling those levers, giving those treatments, we'll get feedback, which can then be used in our model in a new training loop to make better treatments for the next persons. So we got our reinforcement learning set up. And there are different ways of defining reinforcement learning setup, but here we're using context, the features of the user. We're having a certain set of treatments, so it's like multi-arm bandit, so this is the contextual bandit solution approach. The last part in the previous explanation, I also included masks to deal with the counterfactuals, so the final picture after the first issue is like this. So in this reinforcement learning setup, there are two important things. One is that actually the predictions we make on that uplift should actually be quite qualitative. If we predict it wrong, we do the wrong action. Another thing is, when we're doing those actions, we'll get feedback. So it's also really valuable to get quality feedback. And that brings us to the second and the third issue. Of which second is to assume correlation as causation. If we look at a data set, all kind of features and labels, the only thing we can observe are correlations. There are no causations in it, there are just correlations. And those correlations really have predictive power. But what you're going to do is we're not going to observe a system of marketing departments giving campaigns and then some people churning. No, we want to change the treatment. So we want to know if I change this treatment, give another treatment to someone, what will then be the effect? So we're interested in prescriptive power, for which we need the causal link. So I drew here a causal graph where the features influence the retention rate of someone and also the treatment influences the retention rate of someone. Then we are interested in this edge between treatment and retention. And in this setup, the correlation between those two actually is the causation. However, in the past, the company has, of course, done campaigns to specific groups of people. And the model we're currently building, the whole idea is that we learn to give which treatments based on the features of the user. So our model will make a causal dependency between the features and the treatment. And in this case, correlation is not causation anymore, because there's a backdoor between the treatment and the retention. And when we look at the data, we see the combined effect of these two, while we're interested only in the green one. But yeah, so how do we get that one? There are different techniques to get only the causal link, and they all boil down to, well, removing the problem, that red edge between the features and the treatment, the feature-treatment bias. The simplest thing you can do is have random trial groups. So you just you give random sample of your customers one treatment, random sample you don't give treatment, and so on for all treatments. That's nice, simple, straightforward, but that means we're throwing away all our historic data. It's quite expensive experiments, and we just had described a nice feedback loop of a learning system, and now we're just doing random off trials again, so we lose that. Another approach is to change the features. Change features such that you do have the predictive power on retention, but you don't have the predictive power on the treatment. And that can be done by either selecting a few features, so you remove the best predictive features to the treatment, or by doing encoding. There are actually quite fancy ways where you can change the feature set. All your features, you encode them in a new encoding, which is predictive for the retention rate, but not predictive for the treatment. However, you can only do it once, because as soon as you have made a model and an encoding, you recreated the causal link between the features and the treatment. And when you're changing the features, you're restricting your predictive power. So, logically on the third place, causal inference is the way we have to look at, which might be a little bit harder to model, but it actually solves the problem we want to solve. And as causal inference technique, one of them is the inverse propensity weighting. And it works by creating a model which learns how strong that dependency is between the features and the treatment. You can regard it like this. Actually, there are, for some features, like for some age or location, some treatments have a higher probability of being assigned than other treatments. So you get like this density plot. And that density plot is what your propensity model will learn. What you can then do is take that propensity model and create predictions of the propensity of the treatment they got for our whole training data set. And then we're going to use those propensities inversely as a weight. So we weight our training set inversely on probability of the treatment they got. And those weights are used by the model to put more focus on certain samples compared to other samples. So what the model actually observes is not like the density plot anymore, but a weighted density plot. And with this weight, you can actually show that the observed weighted density plot just becomes uniform. And now there's no dependency anymore between any feature and the treatment they got, so that effectively removed the dependency there. But in doing propensity weighting, there are two aspects we have to look at. The first is propensity calibration, and the other one is clipping. Because if you have, for example, some random plot about propensities where the predicted one and the prediction is on the x-axis and the true one on y-axis, what you want is that it's on the middle line, because most classification models focus on ordering. For example, area under curve is just you actually focus on if the order of is good, but not so much if the precise predicted propensity is true to the true probability. So we need to calibrate them to make them more exact, because the propensity, high quality propensities are needed to get a good weight, is needed to get a good model. Another problem is, well, if the weight is 1 divided by propensity and the probability goes to 0, you get some samples with almost infinite weight. So you're going to really overfit on those few samples. Then you can do two things. First is to clip them, so you actually limit all probabilities to be between, for example, 0.05, and then you also have to do it on the other side, 0.095. Or you can say, well, actually, for those regions in our feature space, apparently the distribution of treatments is so imbalanced, we don't have a lot of information in those regions. So why don't we just exclude those regions completely from a data set by putting the weight effectively on 0? So with that, we then change our current setup by making it a causal model using inverse propensity weighting. So we just get a nice new block on the left. And then we are at the third issue. If you have your model, they predict our treatments, actually listening to it and taking the best predicted action. But if well, that would be like a greedy policy or fully exploiting it. We will get feedback on the treatment we did, and we'll learn if it worked or if it didn't work. But we'll never learn if there are better alternatives. So what the model will do is create its own blind spots. For some regions on the feature space, we'll always give a certain treatment. For other regions, another treatment. But we'll never try something else. So what we need to do is we need to balance exploration and exploitation. And that is to be done on 2 dimensions. First, on the treatment to give to a certain person. And then next, to choose which persons in the whole customer base to treat, actually. And for assigning the treatment to selecting the best treatment for a certain person, we can use Thompson sampling. Because our model created this, the uplift rate. For example, this small table. But those values are actually not so much the true uplift point, it's the most likely uplift. And underneath those most likely uplift, there's a distribution of possible uplifts. So, for example, in this case, the email is quite, it has negative uplift, but the distribution is really wide, so we're actually quite uncertain about it. It could have a really big positive impact. And using Bayesian modeling, we actually can get these distributions out of a model. And then what Thompson sampling is, instead of taking that most likely uplift for a certain person, we'll do 3 random draws from each of those distributions. Of 1 random draw for each individual distribution. So you get, maybe for email, we actually get random draw at 0.5 of the uplift. And we combine that with the customer lifetime and the cost of treatment to get the net result. And base our policy on that. If we would have a different customer with exact same distributions, we might get totally different treatments. And what is, you can see this working as well, that in general, we're going to apply the treatments which work best. But some treatments might have some potential. We are uncertain, but actually on the positive side, we'll try some more of those to discover new treatments which might work really well. And with that way, with our feedback loop, our model will actually learn if that potential actually is true or is just model uncertainty, which then can be lessened by retraining. And the next step is, well, as a company, we're gonna, if we determine the best treatment for every customer, we got really big, we got a big set of customers. As a company, you can't give everyone their best treatment. You need to choose some. There's a limited budget. So what you usually do is, normally as you descend, you sort your results descending order. You pick the top, 100 maybe, or 1,000 or 10,000, matters on how much money you have, and treat those. But then again, that can cause us to focus or apply only treatments in a certain area of our feature space. We still want some randomization. That can be done by so-called perturbing the results, where we pick, for example, 5% of all our results, all our customers, and we replace those values by a random value drawn from all the values that we have. So the distribution of values stays the same, but 5% of the values, well, get randomized. And if we look at the histogram, it would mean like for any bin we take, 5% of that will be distributed across all other bins. And that's of course done for all bins. So every bin, any bin we draw, so it doesn't matter if we have 5, 10, or 100 bins, every bin will have almost 5% of values which are randomly drawn from all other, from the whole population. And in that way we can go to the business like, this is really the best list. And then the business has a certain budget, a certain way of finding out how many treatments they can do. They'll go through that list from top to bottom, and it doesn't matter how far they go, they will always have 5% random trials of other people, which then helps us in the model retraining. And then of course, that if it's 5% or 10 or 50 or 1% that we determine, that's of course based on how certain you are that your model works. So then they can, for example, take that bin. Anyway, we have got our final solution where we can then include our exploration and exploitation balancing in by putting in Thompson sampling and perturbating our results, and also using a Bayesian model. And in that way, we also covered our third issue, and that brings us actually to a final complete solution where we have our contextual bandit using uplift modeling, causal inference technique, and Thompson sampling in one nice package, which is I think the best way to prevent churn in a company. And that brings to conclusion. So are there any questions?